Hello and welcome to the MechDesigner YouTube channel. In this video I want to try and explain some motion design techniques that can be applied to multi-axis machines that can improve their performance. The fundamental goal is to reduce the amplitude and frequency content of the power flowing through the machine by optimizing the motion design, implemented by cams and servo motors. This will reduce the forces and torques, giving lower overall component cost, better reliability, less noise and higher throughput. These techniques cannot be indiscriminately applied to all axis motion designs. There will always be a judgment call on how applicable they are and to what extent they will benefit the design, as there is always a trade-off. Nevertheless, we have found this set of techniques very useful when applied judiciously. Motion design is the process of defining the nonlinear cyclical motions of specific elements in the machine, typically cams or servo motors. The mathematical functions defining these movements are usually generated by software. Mechanisms such as forebars can be designed to develop non-cyclical motion, but these are intrinsic to the mechanism's configuration, and I will not be discussing these techniques. I will try and illustrate these techniques using the model shown. I have already chosen the kinematic elements, parts and joints, etc., and also added some solids from SolidWorks into MechDesigner. This simple machine takes ingots from a stack and loads them into an indexing turret. Ingots are then intermittently rotated so that they are accurately presented to a series of tooling stations which perform some operation on the ingot while still. These are not shown. So we can start by writing down the kinematic motion constraints. These are requirements that must be satisfied for the machine to work. I use the word kinematic because they define the condition under which the machine will operate, assuming all mechanisms and machine parts are infinitely stiff, strong, and have available a limitless amount of power to drive them. Another way of thinking is to define constraints without regard to power, forces, and torques. We must name some parts for clarity. So there's the load ingot. This is the ingot which will be operated on during the machine's cycle. The pusher tang, a folded steel tang that controls the deceleration of the load ingot. The turret pocket, this is the scallop on the turret that controls the ingot or the load ingot during the turret index segment. Next, we can identify the nonlinear motion axes. Well, we've got three of these. The stack, the ingot sitting on top of the load ingot, and this motion is defined by the acceleration due to gravity. The pusher plate, this is a folded steel plate that supports and pushes the load ingot and stack, and this can be designed with a motion. And the turret, the indexing turret, which also can be designed with a motion. Next, we specify how they must be kinematically coordinated with each other in time and space. We can start by defining a datum at 0 degrees in machine time or angle, with the stack falling and loading the ingot into the pusher. We can change this later if it is not convenient. I use the term machine angle to refer to some real or virtual crank that revolves 360 degrees every time the machine completes one cycle. In this case, it's convenient to use the camshaft driving the index turret as the machine clock. So we can list the kinematic constraints as 1. The datum. This is the pusher stack support plate clears the stack, so it starts falling. We set this arbitrarily at 0 degrees. Two, the stack has completed falling so that the pusher can start pushing. 3, the pusher can only enter the turret pocket when the turret is stationary. 4, the turret can only begin to index when the pusher is fully advanced. 5, the pusher can only retract when the pusher tang is clear of the load ingot. There are some preliminary dynamic considerations that will also constrain the motion design. These are the minimum time the period of index that we can safely index the turret, and the maximum acceleration we can apply to the pusher crank. The first of these is the starting point, because the minimum time that the turret can be indexed is dependent, among other things, on the motion design selected to index it. More on that later. In fact, there are many design considerations that affect the index time related to cam kinematics, but we will not consider these in this discussion. Again, we'll look at these later. In fact, as will become clear, good motion design creates design loops or iteration that will result in improved overall design. These arise because of the dependencies between motion design, kinematics and dynamics. At this stage, motion design points are very easy to change with the right software. So we will start with a 120-degree index angle giving a 240-degree dwell. The pusher crank maximum acceleration, I will not consider this a limitation at this point. The inertia of this mechanism is less than the indexer, and so I'll assume we can find a motor gearbox combination that will suffice. It's probably time to quickly run through some basics and describe how we can design motion for a specific axis. So I'll use the turret indexer as an example. So here we have a graph showing the motion of the index turret, and on the x-axis is the machine angle going from 0 through the machine cycle to 360 degrees, which spans one machine cycle. On the y-axis we have the position of the turret. The motion is defined by two segments, one dwell and one rise, which shows that the turret moves through 60 degrees, which makes sense as it has 6 equally spaced pockets. We can also look at the velocity and the acceleration and the jerks. These are important as high velocities, accelerations and jerks may be are undesirable for many reasons. So what can we change in this motion? The shorter list is what we can't change. We know that the turret must index through 60 degrees, otherwise the pockets will dwell in the wrong position. But we can change the position of the central node here, which divides the dwell from the rise. So if we shorten the rise segment, we can see the derivatives increase. So what I'll do, what I'm going to do is take this node here, and I'm going to move that further over to the right. So as I do that, of course, the rise segment will get shorter. So I'll move it in 10-degree increments. That's 2. So now it's the dwell is 220, and you can see that if we look at the acceleration, okay, the peak acceleration is currently 12,000 degrees per second. So as I move it another 10, it's now 15,000, 16, 17,000, 20,000. So we can see that all these derivatives are getting larger as we shorten the rise segment length and increase the length of the dwell. So ideally we don't really want to do that. We want to move the node as far as possible to the left. So I'll move it back again, and then we can see that everything calms down, the accelerations get less and less and less. But obviously there's a point at which we will be able to reduce it no more, and the part of motion design is finding out, okay, well how far can we reduce it and keep the acceleration of the indexing turret to a minimum. Acceleration is probably the most important factor of an indexing turret, as that will determine the torque and the forces that are being applied to the various components. We can also change the mathematical functions that calculate the y values for a given machine angle. These are sometimes called motion laws. Changing the motion law varies the ratios between the peak amplitudes of the derivatives, and it also affects the distribution of frequency amplitudes that can be decomposed from the time series by frequency analysis. Generally, we need to keep the power in the lowest possible frequencies, although motion laws with low frequency content tend to have higher peak values in the derivatives. As you can see, there are many motion laws available that have been developed over the years with specific characteristics suitable for most applications. Constant acceleration and deceleration, constant velocity. A lot are based on polynomials. Two of the most common perhaps are modified sine and modified trap. Modified trapezoidal has the advantage of slightly lower acceleration than the modified sine. The modified sine is generally used in systems which have a certain amount of backlash. But the law that we found to be the most useful or ubiquitous is the flexible polynomial. You can specify the flexible polynomial with a total of 8 boundary conditions, 4 at the start and 4 at the end, so in position, velocity, acceleration and jerk. This gives you sufficient control over the polynomial to be able to model most of the other segment types in this list, apart from perhaps the position list. The position list will give you the opportunity to put a list of numbers, so you can put any function you like really using that particular facility. You can also reduce the, if you don't specify a boundary condition, then the certain orders of the polynomial will be ignored. For example, in this one I've only got 4 boundary conditions specified, so there will only be 4 orders, 4 powers in the polynomial which are used. So just to summarize where we are, we've got 3 motions in our model. We have the crank, which is a return model motion. So there's a long rise, short dwell, and then a return. So this is the push. This part is the push of the box into the pocket. Then a dwell to wait until it's able to retract, and then the retraction, and then a dwell again, so that the box has already fallen in front of the pusher before it can start repeating the cycle. Then we've got the box fall. Okay, this we model with just a constant acceleration. So if we look at this motion law, we can see that we've got position, put the velocity in, and the acceleration. Then we have constant acceleration. Not sure why the velocity isn't showing. There we go. So we have a constant acceleration, which gives a constantly increasing velocity and a quadratic increase in position, as you'd expect. And then finally we have the turret motion, which is a simple indexing motion accompanied by a dwell. So the goal now is we want to try and get as smooth as possible motions, or as motions which will reduce, will have a small effect on the forces and torques on the machine as possible. So we can start doing that now. I'm going to start by talking about jerk and what power controlling it gives us to improve motion design. So if we return to the indexing motion of the turret, and we look specifically at the rise motion of the turret, and look at the position, the velocity, the acceleration and the jerk, what I want to do is experiment a little bit by changing the value of the jerk at the start and end positions and see what happens to the acceleration and velocity. So if we, up here I've got the control points for the segment. It's a flexible polynomial, so we can control the jerk, and at the moment the jerk is some huge number, 400,000 degrees per second per second per second. So I'm going to take this down to 0. At the moment the acceleration is about 8,000, just under 8,000 degrees per second. So I'm going to take this to 0 and this to 0. So both ends now I've taken the jerk right down to 0 at both ends of the segment, and now I'm going to move. I have to move the cursor here. This is the cursor showing, and I want to select the peak acceleration. So I'm going to move this back to that's not the peak accelerate. That's not the peak jerk. Peak acceleration. Do apologise. So I'll move that back to what we think the peak acceleration is. Remember, it was just under 8,000 before. So now I've turned the jerk on, and now it's 10,000, almost 10,400. So a consequence of increasing the jerk is that of reducing the jerk at the boundary to 0 is that we've increased the acceleration from just under 8,000 to 10,400, which is what 20% increase. So you'd think at first, well, we don't want to do that then, do we? Because that's obviously going to increase the torque on the followers and the torque requirement of the motor, and therefore probably mean that we'll have to build or buy a bigger indexing box, which is not good. But we have to look carefully at what else it's done. Well, the first thing is the motion is inevitably smoother. We've reduced the frequency content. That's basically what happens when the jerk. If you have high jerk, it does tend to excite vibrations. So especially discontinuities in jerk. So ideally, you want to. It's good for reducing vibrations to reduce the jerk, which we've done. We had a discontinuity in jerk. Remember when we started. So that's a positive. But the other thing that we should notice is that the jerk, if we look at the displacement, then it looks to me as if nothing really happens in terms of displacement until quite some time. If we actually look at the value of the displacement at the boundary, okay, the start position is 0. Well, if we look at if we move the cursor closer to, I don't know, say 10 degrees away from where the boundary is, we notice that it's only moved 0.16 in 10. What's that in? So 225. Okay, the boundary segment starts at 210, and we're at 225, the cursor position. So that's 15 degrees into the motion segment, and yet the position has only moved by 0.163 of a degree. So it's hardly moved at all, and we can exploit this because what that means is that if it hasn't moved, it's effectively a dwell. And if we're working with a packaging machine, I think tolerances of 0.163 of a degree, well, obviously it depends on the radius of the turret, but I know the radius of the turret is 100 millimeters, so that would be a very, very small, that would correspond to a very, very small displacement in millimeters. So what this means is that we can elongate, we can lengthen the segment without any serious penalties. Because if we lengthen the segment, if we lengthen the segment, then we reduce the accelerations. So we're gaining the advantage. We can keep the acceleration roughly the same, but we can make a much, much smoother motion. So what we can try and do is widen this segment and reduce the acceleration. As we widen it, the acceleration will reduce the acceleration down to 8,000 degrees per second, and at that point see what the displacement is at 210 degrees. And if the displacement is manageable, and we can test that by looking at the model, then this would be an improvement in the motion design. So I'm going to do that. So the moment the width of the segment is 150. So what I'm going to do is start moving this node here over to the left to lengthen the segment, and as we do that, the acceleration should reduce. So I'll just start doing that. So so the x-axis, I think it's this one here, so I'll just start moving this, maybe 10 degree increments. Okay, so we'll move that 10. I'll move it 20 and see what happens. Okay, so I've moved it 20, and let's just see what the acceleration is at this position here. So I'll drag this over here. Where are we? Look, I've moved it 20 and we're at 8,079, which is pretty much where we were before. And now we can look at the displacement at 2010, which you remember is where the segment started. So if I move this to look at this, move the cursor to look at the displacement at 2010. So I'll do that. I'll just type it in. 210. Then the displacement is 0.3 degrees. Okay, so I'll leave it there, and we can now have a look and see what this looks like in the model. Okay, so now I'm going to cycle the model and see what happens. So hit the start button. Now it's cycling pretty slowly, so I'll just move it a bit faster. So when we go, okay, it doesn't seem to be any problem at this speed. But now we can see there's a clash between the pusher plate and the turret. Okay, so I've now advanced the the machine angle to 190 degrees, which is the point at which the turret should start to index. Now if I move the model forward now, say, I don't know, a degree at a time, you can see that the pusher plate isn't fully home, and yet there's hardly any motion in the turret at all, and this is because of the low jerk at the beginning of the segment. Just start to see it moving now. But the pusher plate is now home, and that's at 210. So there we've got 20 degrees of motion, and the turret is hardly indexed at all. So I think this is perfectly acceptable. Just indexing it for 230, 240. Now the problem now what we can see is that the pusher plate fouls unpleasantly onto the turret. So we've got to start thinking about the motion design of the pusher plate next to avoid this problem. Okay, so we're looking at the motion profile for the pusher plate, which has 4 segments in it. This is the forward section. This is the forward motion running from 0 degrees to 240. There's a short dwell of, I think, about 20 degrees, and then the return, the retraction, and then there's another short dwell to allow the the ingot to fall. So we know that at 210 degrees, that was the old start of the turret motion, which is about here. So now we've moved that to 190 degrees, which is probably about here. And we can see that at this point, the the pusher plate has got quite a large motion to complete. But we're not worried about that because now the turret is starting at 190, but it moves so slowly that even though this has got quite a large motion to complete, the turret is still stationary when we get to very, very, well, 240 really. But we need to be able to retract the pusher plate earlier, so to avoid it fouling on the turret itself. And there's a little dwell in here which is probably completely unnecessary. So what I'm going to do is I'm going to delete that dwell like so. And this is 240, and then I've got to lengthen this segment, so by whatever that was, I can't remember what it was now. I should have checked really, but so I'll go to the segment editor here, and okay, this segment is 100, and the full motion length is still 360 actually, so it's stretched it. Okay, so we can leave it like that and see what we get. Okay, so now I'll move this out the way. Oops, move that out the way. And we can have a look and see if we're still getting this fouling problem. So I'll start to cycle. Here we go, quite a quick cycle speed, just to see where we are. I've taken about 10 degrees out, okay, and the retraction a little bit earlier, but it's still fouling, so we've still got a problem with this. So maybe we've got to, we're moving the pusher in a bit too slowly. And if we look at it, it's a fairly low acceleration pushing in with a higher acceleration when it retracts. So I think we need to balance the pusher plate motion better. So this is the pusher plate motion again. We've removed the dwell. But now let's have a look at the velocity and the acceleration. So I'll just show the velocity and the acceleration. And we can see that there's a serious asymmetry in this motion design. So we've got relatively low velocity of 100 degrees per second on the forward stroke, and then on the retraction, it's at about 2,300. And this arises because of this asymmetry in the motion. So this section is much, much longer than this segment, sorry. And as we were saying before, the shorter the segment, the higher the accelerations. In fact, the acceleration varies with the square of the amount or the factor by which the segment has been reduced. So we know that from looking at the motion before that we actually want to move this point further to the left, because that will help us, or we think it'll help us, get the retraction earlier. Or will it? There's a complexity here, but let's have a look. Right, so what I'm going to do is try and balance the motion better. I'll just move this back 10 degrees and let's see what happens. Okay, so let's go into, I'll choose the node editor and I'm just going to move it back 10 degrees. So there we go, 10 degrees. It's now at 240. Sorry, is that? Yeah, 240. So let's have a look. In fact, that's returned it to where it was originally. I didn't realize when I deleted the dwell that in fact it lengthened the previous segment. So that's returned it back to where it was. So let's have a look now at how we're getting on if we look at the model again. So here we go, I'll cycle this. Pusher advances, pushing the ingot in, and okay, it seems okay. And this time it's a little bit better, still fouling slightly. So maybe we can get it even, we can move the node even further to the left. Okay, so perhaps we can try something very radical. I can't think of a reason at the moment, although one will probably arise later, why we can't move this node in such a way that both of these segments, that is the advanced segment and the retraction, are of equal machine angle length. Then they'd be perfectly balanced. That's got to be a good thing. So I'm going to do that, and then we'll have a look and see what the implications are on the model. So I'll go to the node editor, and I'll move this node now right the way across to balance the acceleration. You can see the accelerations and the velocities are now evening up. So we've reduced the maximum amplitude of the acceleration, which is a good thing, because that'll, as we know, will reduce the forces and torques that have to be sustained by components in the machine. So we can now cycle the machine with this radical new pusher motion and see what the implications are. Now we'll see straight away that the retraction is happening much too early. However, the push is fine. It doesn't seem to be causing too many problems, the insertion. It's just the fouling of the ingot on the retraction. So what have we got to do? Well, we used to have a dwell in the motion, but maybe we can use another trick to introduce a pseudo dwell. So if we look at the motion at this node, we've sort of got a pseudo dwell, because do we really mind if the pusher moves by a small amount? Not really, because we know that if it's only moving a small amount, it's effectively a dwell. But perhaps we can make this dwell even more exaggerated, or lengthen it, or this pseudo dwell, we can lengthen it by using the trick that we used before by controlling the jerk. So for example, if we bring in the jerk, now we notice there's a discontinuity in the jerk here, which is again not a good thing, as that will potentially excite some vibrations depending on how stiff the servo mechanism system is. So what I'm going to do is turn a thing called flow on here, and I'm going to make the jerk match. The way I can do that is, I think, with the node editor. So I'll bring the node editor up here. So I'm going to edit this node now, and I want to specify I'll just turn the flow on here and see what happens. Okay, so see what happens. That's brought the jerk here to match, to flow. I'll I'm not sure I want it to be a non-zero value here, so I'm just going to edit, specify it here and make it 0. So I just right click there and put that into 0. Ooh, that's starting to look a bit better. So now you'll notice that we've got a much larger pseudo dwell. We could actually go in the analysis and try and figure out how much we think, how we define our pseudo dwell in terms of displacement. But for the purposes of this exercise, I think we can just take a visual cue that is much flatter than it was before. So now we can have a look and see what effect this has on our model. So I'll drag this out of the way, and we can cycle it again. I'll run that. Okay, and so the pusher is advancing. But now this is going to delay this is really a tiny move. It's still not quite, it's still fouling on the ingot. So we've got two options now. We can either move the pusher motion, the node of the pusher motion when it's at its most advanced position. We can delay that, but then that would undo all the good work we've done balancing the motion. But we have another option. It's possible that if we look at this, we can advance the indexing turret motion slightly, because it looks to me as if there's plenty of time to push the motion, to push the ingot in before the turret starts to index. So let's experiment with that. So back on the indexer motion, and what I want to do is advance this whole motion really, so move everything further to the left. The way I can do that is by using this node editor, and there's a little box in here which says motion start. So I want a negative motion start. I want this motion to start earlier. So I'll just move it maybe 20 degrees. Let's see, maybe too much that, I don't know. Well, let's find out. I've moved it 20 degrees anyway, further to the left. So now we can drag this out of the way again and have a look at the model and see how we're getting on. So I'll home this and cycle. So if we go pushing in, this is the important bit. Is it going to, oh, it looks okay, that looks very good. I'm quite pleased with it. There's still plenty of time, so I think we can move it. Oh, it's retraction still catching a little bit on the return. So in it goes. Okay, so I think there's still time. We can perhaps advance the indexing turret even further, but it is just fouling on the end here. Just if you watch this, insertion, turret indexes, and then it just catches the pocket. The pusher just catches the pocket here. Now I could, I suppose, increase this scallop, the size of the scallop here, but maybe that is not such a great solution at the moment. Let's make the assumption that we don't want to do that. So maybe we can advance the timing even further. So I'll stop it. Let's move up this motion here so you can see what's going on. Go to the node editor and let's move it forward another 10 degrees. So this is going to be minus 30. Okay, and back to the model and cycle. Still okay, and we retract. Ooh, oh no, that's worse, isn't it? What's happened there? That's, maybe we've not got it quite right. I've gone the wrong way, I think. Yeah, I've gone the wrong way. So what I need to do is just stop this and drag back the model again. Get the node editor, and rather than minus 20, what I'm going to do, minus 30, sorry, I'll move that up to minus 10. Let's have a look at that, see how that gets on. Hit that out. Okay, and let's drop this down and try it again. So advances, pushes the ingot in, that's okay, no problem, and then it indexes off. Oh, I think that's just missing, I don't know. The answer probably lies another 5 degrees earlier for the turret motion. So I'm just going to do that now. Stop. Okay, I've now advanced the turret motion to 15 degrees, and I think this is pretty good now. So it clears, yeah, that clears, everything clears. Oh, maybe just catches the corner. We might have to put a little chamfer on the end of the top of the pocket, but I think that's pretty good. Yeah, the ingot clears, the tang, yeah, it's a bit close. If there's some vibrations, you can imagine that hitting, so it's a bit tight. Nevertheless, I think for the purposes of this exercise, that's complete. Okay, I think I'll finish this video here. It's getting a bit long. Just to summarize, we've gone through motion constraints, where I've talked about the two different types, kinematic and dynamic, and it's a very good idea to get a clear idea of what these are before you begin the motion design, because there's a danger with motion design that you tend to over constrain because of just things that you forget about, and you forget that you can actually free some aspects of the motion design up. For example, the turret in this example, I was able to move the turret index motion back and forth without any serious consequences. Then we've gone through an example. I've shown an example, a very simple example, just two design axes, and have considered two tricks. The first of which was the pseudo dwells, which you can achieve using control of the jerk in the start and end of motions segments, particularly the flexible polynomial. And the second I've looked at balancing motions, and this is quite important if you want to try and reduce the overall acceleration or the peak acceleration amplitudes and velocity amplitudes. Just make sure that your motion segments have similar peak accelerations, usually by matching if it's a dwell return, if it's a rise return, by matching the segment widths. Of course, if you're picking up objects and increasing the mass substantially on a forward stroke, as we are in this particular example, then that might not be the perfect solution. You might need to consider the torques directly, and I'll look at this particular issue in the next motion design video. Thanks for listening, and please subscribe, and I'll carry on trying to produce videos. I'm not going to say every week, but certainly every year. Cheers.